So in class last Friday, we were dealing with BJT current mirrors. We're still looking at BJT current mirrors. And so we worked an example problem that showed that there was potentially a significant amount of error introduced when we were making multiple copies of our reference current. So now we're going to talk about how we might avoid introducing all of that error. Right, so here's our, sorry, this should be I copy. So here's IC1, IB1, IBref, ICref, and up to this point, we were diode connecting that transistor so that those base currents were supplied by our reference current, which was in turn what was causing our error, or at least contributing most significantly to our error. So what we're going to do is we're going to add another transistor, and that transistor is going to be responsible for supplying those base currents. So effectively what we're doing here is we are adding in an emitter follower transistor and using it as a current amplifier. So we're going to call this guy Q sub F. Like so. And so let's call this current IBF. And this current IEF, like here, and kind of work through some things, right? So why is this advantageous? Okay, so we're using this effectively emitter follower amplifier as a current amplifier so that we know that the base current is going to be significantly smaller than our emitter current for this amplifier. And the emitter current is literally just supplying base currents to Qref and Q1, which means the base current IVF is going to be very, very small because the current needed for these base currents combined is also very, very small, right? So a simple current amplifier is going to take care of this. Great. We could go through the work here and figure out what our error would be for this particular configuration, but instead, let's look at what our error looks like for the example problem that we worked at the end of our last class meeting. So that's kind of an apples to apples comparison, right? So let's say that this is the circuit that we're looking at. If I'm not mistaken, this guy was twice AE. This Qref down here. This guy like so. Call this UF. Let's move this down here. Q1. This guy was 3 times This guy was 5 times. We can pull our base current from over here, where this current was I copy 1. This current was I copy 2. And I'll go ahead and label the currents that we'll be paying attention to here. So this will be IC2, IC1. Actually, I've been using blue for currents. IBref, IEF, IBF, ICref, like so. And I think I forgot to label this guy over here as Q2. All right, so we can make a couple of quick observation things here. The base emitter voltage for our reference transistor Qref, as well as our transistors Q1 and Q2 are all the same. So from that, we can say that IC1 is still going to be 3/2 of ICref, and IC2 is still going to be 5/2 of ICref. Are we all okay with that? Nothing really changed there. Okay. Now we can apply Kirchhoff's current law at this node that I'll circle in red. Okay. And so that's going to give us the relationship IEF, so our emitter current for our follower transistor, is going to look like IBref plus IB1 plus IB2. So that is going to look like 1 over beta times ICref plus 3 ICref over 2 beta plus 5 ICref over 2 beta. And on the left-hand side, I'm going to make a small change here, and we'll see why in a moment. I'm going to call this guy beta plus 1 over beta ICF. So I'm just putting it in terms of the collector current for that emitter follower transistor. I can lump things together now. And so that's going to give me beta plus 1 over beta ICF is equal to ICref. So let's see, 1 over beta could look like 2 over 2 beta. Plus a factor of 3 over 2 beta. Plus a factor of 5 over 2 beta. Add all of that stuff together and it looks like 10 over 2 beta. And here we could say that ICF is then ICref times 10 over 2 beta times beta over beta plus 1. This beta cancels this beta, and 10 over 2 is just equal to 5. So that's going to look like ICref times 5 over beta plus 1. Anybody got any questions, comments, or concerns regarding the results of our KCL at that node where our 3 base currents are tied together? Fairly straightforward. Yes, James.
I have a question. We were to see a circuit similar to this. We have some of the transistors are driving voltages, some of them are accepting voltages. How do we know which one would be, which one is the reference? For example, if we had another current source on IC1, how would we know it's not driving?
So if you're saying, just to be clear here, if I put another current source up here, is that what you were suggesting?
Just as an example, we did see something like that. How do we know IC1 doesn't dictate the reference?
If you had another current source up there, you'd no longer have a current mirror because you'd have 2 currents forcing things to happen instead of just the one, right? So the reference current is always going to be the one that's labeled literally as a reference for the short term. I guess I don't fully understand your question.
It's just like we're assuming that the base voltage is base voltage less than current driven by the current present. But how do we know that whatever is going on the other transistors doesn't also drive everything in that red zone? How do we know that Q-ref is not a current source like the other transistors?
Okay. So if I labeled, let's say that I call this guy Q1, this guy Q2, and this guy Q3, so that none of them are labeled explicitly as the reference. Is that going to change my ACL relationships or my KVL relationships or anything like that?
No, sir.
So we are not relying on anything in particular here about one driving the other or anything like that. We're doing all of our analysis just based on using KCL, KVL, and effectively seeing what shakes out, with our ultimate goal being to figure out what the relationship between any of these copy currents up on the right-hand side are in relation to that reference current source on the left. But we're not explicitly stating anything other than by inspection, because there's a base emitter voltage between here and here, and that exact same base emitter voltage must be here, because the bases are tied together and both of the emitters are on ground. And this base emitter voltage between here and here, all 3 of those have to be the same. That's what allows us to make the relationship that, assuming early effect is neglected, our collector currents have to be related to each other. But that doesn't have anything to do whatsoever with the reference current. That's just how the circuit is configured. Does that make sense?
I think so. I guess I'm kind of curious why Q-ref, we're using it at the beginning, we said it as a sensor, right? We're sensing the current and we're using that to force the other transistors to drive them.
That was, yeah, so I said that in as much as we were trying to figure out how to piece together how to duplicate the current. But as soon as we put that diode connection in there, that kind of messes things up, because not all of that reference current is flowing in to, like, not all of IREF is flowing into the collector of QREF. So now we're relying on our KCL and KVL relationships to actually figure out how this works, instead of saying explicitly that IREF there is driving that resistor, because realistically that IREF there is driving all the transistors here. in some shape or form, or at least in the previous example, because it was supplying base currents to literally everything. And any BJT transistor can be thought of as a current controlled current source. IB is in, beta times IB is the collector current. That's our current controlled current source model. We are using the voltage controlled current source model where the base emitter voltage is what's providing our current. But anyway, I think we're talking each other in circles. Yeah. All right. So all right. So I've done KCL at this red node here. Now let's do KCL at this load here, or excuse me, at this node here, okay? So now we have a current of IREF flowing in, and that is going to have to equal to ICREF plus IBF. Just so that we're clear, let's scroll back up. So this current flowing in is equal to this current plus this current flowing in. Right? Nothing remotely fancy going on there. We know that IBREF is related, or excuse me, IBF is related to ICF. So we can simply make that substitution really quickly. So we're going to have ICREF plus ICF over beta. And then substituting in our relationship for ICF that we got by applying Kirchhoff's current law at the node I circled in red, this is going to look like ICREF plus ICREF times 5 over beta times beta plus 1. And now I can just lump those two terms together by saying that the ICREF by itself could be multiplied by beta over beta plus 1 divided by beta over beta plus 1 so that I have a common denominator, right? So that's going to look like, put it over here, IREF is equal to ICREF times beta plus 1 plus 5 all over beta times beta plus 1. And we know, need to come back up here and use these relationships. So I copy 1 is equal to three halves ICREF. And so that's going to be, let's see. ICREF could be expressed as IREF times the reciprocal there. So beta over beta plus, or excuse me, times beta plus 1 over beta plus 1 plus 5, like so. And so that would be 3 halves IREF times beta plus 1 over beta times beta plus 1 plus 5, where this bit right here is effectively, once again, our error. Everybody okay with my algebra? So if we do 1 minus this quantity, we wind up with an error of 0.0495%. Significantly lower error than what we had earlier. So previously, I think we had an error of somewhere in the ballpark of 3.75%. Now we're down to less than a 1/20th%. So using that emitter follower current amplifier there to supply our base currents, it provides a very significant increase in the performance of our current mirror without adding too much complexity. Okay. So let's look at the output resistance of one of these current mirrors. So the reason why we're going to pay attention to our output resistance here is because this is effectively providing bias for an amplifier. And so the resistance that this thing contributes, we know should have some effect on the gain of an amplifier. Okay. So let's look at our basic current mirror. And see what this looks like. And then from that, we can make a couple of quick assumptions. So this is our basic representation of our current mirror. And its small signal model should look something like this. Okay. So here's R naught for the transistor on the left. And because our transistors are matched, I'm not going to bother putting further subscripts here because they're all going to be the same thing, right? Oops, this should be current source. So this will be GM VBE. And here's going to be R pi, where this node right here is the collector of the left transistor. This node right here is the base of the left transistor. And because we have a diode connection, that's why we have this wire right here. Our emitter node, which would be down here, is at ground. Now I'm going to do my right-hand transistor. So there's R pi. GM VBE. R naught. Here's my collector, my base. My two bases are tied together. Grounds are tied together. So this is my voltage VBE for both of those transistors. And over here on the right-hand side where I'm running out of room is where we might apply our test voltage source. Okay. So let's apply Kirchhoff's current law at this node. So the current flowing through that left resistor R naught would look like VBE over R naught. Then I'm going to have a current of GM VBE down. I have two R pi's effectively in parallel with each other. So that's just going to look like R pi over 2. So that's going to look like twice VBE over R pi. And these guys all add together to make 0. Are we okay with this KCL expression? Okay, so let's see what this implies. If I factor out VBE, I'm left with 1 over R naught plus 2 over R pi plus GM is equal to 0. So let me ask you guys a question. Is R naught going to be 0? Never. Literally never. Is R pi going to be 0? Also literally never. Is GM going to be 0? Not if this is carrying any current, and it should be on account of it's a current mirror, so that's his job. So everything inside the brackets will never be 0. So how is it possible that this expression would equal 0? VBE was 0. Absolutely right. So VBE must be 0. So what's our output resistance then? R naught. That's it. What if we had transistors in parallel? Yeah, not remotely difficult, right? If we have multiple transistors in parallel, it's just the number of R naughts in parallel. That's it. So the current mirror, as we've learned it here, has the exact same output resistance, as it were, as just a simple single transistor current source, which should make sense because realistically, that's what we're using it as. Okay. All right. Let's look at PNP current mirrors really quickly. Okay. So all of the current mirrors that we've dealt with here, where we had an NPN current mirror, we were effectively, let me draw a simple amplifier here. So let's say that we had a simple common emitter amplifier where here is our supply voltage up top. Here's our input. Here's our output. And then here's the current source that's effectively buying this thing, or biasing this thing. Well, this is our NPN current mirror, right? So what if we wanted to bias a circuit like this? This guy up here would need to be a PNP current mirror, right? So an NPN current mirror is always going to effectively be drawing a current down towards ground. The PNP current mirror is always going to be drawing a current out of our supply voltage. Okay. So how do you guys think we might implement something like this? So short answer is it's going to be effectively the current mirror that we just dealt with, but kind of turned upside down. So here's our supply voltage. Here's our Qref. Here's our IREF. Here's our I copy. Here's our transistor Q1. Okay. Same basic topology, just everything kind of flipped upside down. Now, where do you think this current IREF is going to come from? So for our NPN current mirror, our current IREF effectively came from that rather large and bulky band gap reference circuit. Would we want to implement another large, bulky band gap reference circuit? Probably not. The whole point of the current mirror is to avoid having multiples of those in our circuit. So instead, what we're actually going to do is we're going to use an NPN current mirror to bias our PNP current mirror. So we're going to have something like this. So here's our reference current from our band gap reference generator. That is here. We'll throw a transistor up here. All of these are at VCC, like so. We could diode connect these transistors, in which case we're going to see a significant amount of error, because effectively the current flowing through this guy right here. Let me label this. So this current IC1 is serving the role as the reference current for the PNP current mirror. And we know that IC1 has a little bit of error in and of it inherent to it because IREF is supplying the base current for that. Right? So in order to avoid that, we might use an emitter follower current amplifier to provide those currents. So we could have something like this. Where this would be QF, QREF N. Let's call this QREF P. Actually, let's leave that as Q1. This will be QREF P. This will be Q2. And this is I copy 2, except that we might want to put an emitter follower there as well to eliminate the error on that side of the device, right? Actually, let me sneak it in here. I'm getting mixed up. There's my base. There we go. Something like that. So I have a homework problem that I'm going to ask you guys to work to find the error in a system like this. I'm telling you explicitly, break the problem up into two stages. Figure out what's going on with the NPN stage first, and then just treat that like a current source, and then do the analysis on the PNP side. If you try to do it all in one go, it's going to get terrifyingly gross with all of the algebra that it entails. This is realistically what a good PNP current mirror would look like. All right, so let's make our lives way easier and look at MOSFETs. All right, so for the MOSFET current mirror, we're not going to do any kind of explanation as to why it's connected the way it's connected. We're literally just going to replace our BJTs with MOSFETs. Okay? We understand effectively what's going on because we have a relatively good grasp of how the BJT current mirror works. So our circuit would look something like this. Here's our reference current. Here's our MOSFET MREF. And we'll diode connect these guys. So in an amplifier, or excuse me, in a current mirror like this, we know that our gate currents are effectively zero, right? So this current is 0 amps. This current is 0 amps. Means this current is 0 amps. So from that, we know that the current that's flowing into transistor MREF is just IREF. We have this voltage, VGS ref, that must be identical to this voltage, VGS1. Yes. Because we diode connected the BJT. It's literally just replacing the transistors from a BJT to a MOSFET. Yeah, that's it. Another reason, other than my snarky comment there, is remember that for a diode connected device, it forces this guy to always be in saturation. So that's another reason to do it. So since both of these devices have the same VGS, this current I1 is ostensibly going to be equal to IREF as well. There is, however, a caveat here. Okay? The caveat is that the transistors, so we could say that I copy 1 is equal to IREF if the aspect ratio of the reference transistor and the aspect ratio of the copy transistor are the same. Which pretty obviously tells us how we're going to get around to scaling our currents, right? We're just going to change the aspect ratios of each side of this device. So if we want our copy current to be smaller than our reference current, we make this transistor physically wider. If we want our copy current to be larger than our reference current, we make this transistor physically wider. Very, very easy and straightforward. Is there any reason for us to, and by the way, all of these relationships that we've just talked about, we are assuming that channel length modulation is neglected, but that is obviously going to have some impact because if they have different VDS values, then the ratio of the current is going to be slightly different. Is there any reason why we would ever need to connect a source follower transistor to a MOSFET current mirror? No, not at all. So it doesn't get more complicated than this for a simple current mirror. What if we wanted a PMOS current mirror? Same thing as we did earlier, just replace all of the BJTs with MOSFETs. So MOSFET current mirrors are much, much easier to deal with because we don't have to worry about the base currents and all of that kind of good stuff. So that begs the question, why do I care so much about BJTs? BJTs are arguably, and actually it's not really much of an argument, much better transistors in every conceivable way than a MOSFET, except for cost, right? MOSFET transistors are in such widespread utilization simply because they are so cheap and easy to manufacture. They do not electrically perform better than a BJT at all. It's just, they're cheap. So that's why we use them. So having an understanding of why and how all of the BJT stuff works will make you a better engineer overall because you can design stuff for a specific application. And then you find out, can I do this with a MOSFET later on? All right. What do you think the output resistance of the MOSFET current mirror is going to be without doing any math whatsoever? R naught. Yep, great. Okay. So now let's talk about different current mirror topologies and why we might use them. So the first one that we're going to look at is the Wilson current. It's going to be rather similar to the simple BJT current mirror, except that it's going to add one more transistor. So we're going to have something that looks like this. Here's our reference current. Here's our copy current. And this time we're going to diode connect this side. So let's call this guy Q1, Q2, and Q3. And let's go ahead and label some current so we can figure out how this guy works. Okay. So this is going to be the current IC1, IB1, IB2, IC2. Here's our emitter current, IE3, our base current, IB3, and our collector current, IC3. And this will be our base emitter voltage, VBE1. Here's our base emitter voltage, VBE2. Right? So what can we infer just by inspection here? Well, VBE1 must be equal to VBE2 because those bases are tied together and both of the emitters are at ground, right? So since VBE1 and VBE2 are the same, that means that IC1 and IC2 should be the same. And IB1 and IB2 should be the same. Again, we're neglecting any contributions of the early effect here because it's just going to make the math ludicrously gross as we saw earlier. Okay. So if we apply Kirchhoff's current law at this node, we can see that the current IE3 is equal to IC2 plus IB2 plus IB1 IE3 is just going to be beta plus 1 over beta times IC3, which is just our copy current there. And so we are going to have IC1 times one plus 2 over beta. Where I'm just saying that this IB2 is IC1 over beta. This IB1 is IC1 over beta. And this IC2 is just IC1. So we all okay with where came from that stuff? All right. And so now from this, I can do a little bit of rearranging. And I could say that IC1 is I copy times beta plus 1 over beta times, let's see, let me expand this out just a smidge here. So that would be beta plus 2 over beta. Right, calling one beta over beta and then having a common denominator. So that's going to look like beta over beta plus 2. These guys cancel each other out. And that's just I copy times beta plus 1 over beta plus 2. we apply KCL at this node, we wind up getting IREF is equal to IC1 plus IB3. Where we can make a simple substitution in for IC1. We know that's just I copy times beta plus 1 over beta plus 2. What's IB3 in terms of I copy? I copy over beta, absolutely right. And so now we're just going to do a little bit of algebra to clean this thing up. This. So how am I going to make this less gross? Let's look at that. So I'm going to have beta plus 1 times beta over beta plus 2 times beta plus beta plus 2 over beta plus 2 times beta, like so. And that gives me I copy of beta times beta plus 1 plus beta plus 2 divided by beta times beta plus 2. And therefore, I copy is equal to IREF times the reciprocal of that ratio. So for beta is equal to 100, the ratio of I copy to IREF comes out to be 99.980%. For beta is equal to 50, that same ratio comes out to 99.923%. For beta is equal to 10, which would be a garbage transistor, that ratio comes out to be 98.361%. So the principal advantage of using a Wilson current mirror over a simple current mirror is that it is largely independent of beta. Can be a pretty significant thing. Another reason why we might want to use a Wilson current mirror is that it actually gives us a significantly larger output resistance. Why do you think having a larger output resistance might be important? In the best case scenario, we would be biasing these integrated circuit amplifiers and stuff like that with an ideal current source, where an ideal current source supplies some amount of current and its internal resistance is infinitely large. So the larger that we can make R out, the more like an ideal current source our transistor current source is going to behave, right? So having a very, very large output resistance is going to be very good. When we look at the Cascode amplifier, which will be, I think, on Friday, I'm going to teach you guys a different way to find the voltage gain of an amplifier that's using a quantity called the short circuit transconductance, which for some amplifier topologies is a little bit easier to figure out, and the output resistance. We're going to find effectively that the voltage gain of any amplifier can be expressed as just the product of R out and the short circuit transconductance. So the larger that we can make R out in any case is going to give us an increase in our voltage gain effectively. So a couple of different ones that we do. Okay. So small signal model for this guy is going to be kind of big and gross because it's 3 transistors, right? So this class ends at 10:45, right? Okay. So let's put one guy down here. So here's transistor R01, or excuse me, resistance R01. Here's GM1, VBE1. There's a ground. RPi1, VBE1. RPi2, VBE2. GM2, VBE2, R02. Let me just label some things here. So this is the collector of transistor 1. This is the emitter of transistor 1, the base of 1, the base of 2, the emitter of 2, the collector of 2. Up here, we're going to put that transistor 3. So here's RPi3. GM3, VBE3. Here's the voltage, VBE3. R03. The emitter of transistor 3 is tied to the collector of transistor 2, so I'm just going to put a short circuit right here. The base of transistor 3 is tied to the collector of transistor 1, so I'm going to put a short, oops, didn't draw that quite long enough. Like this. So this is B3, E3, C3. And then over here, I'll put my test source. Actually, let's do a voltage source. And all right. Okay. So I'm going to label a couple of currents here. We're just trying to kind of sort what's going on because, like I said, this is pretty large and gross, right? So our test current IX is going to flow into the collector of transistor 3. It's going to split between that dependent current source GM3, DBE3, and that resistance R03 before recombining at that node C3 that I have labeled, excuse me. And then it's going to split up again. And so let's call this current that flows this way I1. So that's just the portion of IX that splits off and flows towards transistor 1. And we'll call this current right here I2, which is just the portion of our test current that splits off and flows down through transistor 2. Okay. So from this, we can say that IX, excuse me, is simply I1 plus I2. Oh, actually, I have made a couple of mistakes here, so let's fix some things. So the first mistake that I have made is in my drawing. Maybe this is what you guys were whispering about. Transistor 2 was diode connected, but I didn't diode connect it in my small signal model. Okay, so that should be connected because we have a diode connected transistor, and because my grounds are at the same potential, I could connect these two guys as well. So marketer. So let's look at current I2 here real quick. Okay. So what do you guys think the resistance seen between seen by current I2 is going to be? Do you think that dependent current source is going to contribute anything? I think it does. Right. It's going to contribute a 1 over GM2, right? Because we have a diode connected configuration. So we can say that the voltage VBE2 is equal to the current I2 times R pi 1 in parallel with R pi 2 in parallel with R naught 2 in parallel with 1 over GM2. And this will be approximately just I2 divided by GM2. So we're making an assumption here that should be true the overwhelming majority of the time, that the resistance 1 over GM2 is smaller than all of those other ones. And so when we put all of those things in parallel, it'll be about the same as 1 over GM2. Okay. Now, we can see directly by inspection that VBE2 and VBE1 are literally the same voltage because our bases and R are together. So the current that is being supplied by the GM1 VBE1 source, right? So we could say that GM1 VBE1 is going to be GM1, or at least approximately, over GM2 times I2. And if transistors 1 and 2 are matched, then their transconductances should be the same. So GM1 times VBE1 is approximately equal to I2. Sorry, I'm having difficulty following my notes. Give me just a moment. So VBE2. All right, well, I'm just going to start writing this stuff down and I'll sort it out here so that we're not wasting too much time. So in my notes here, I have applying KVL2 to the left-hand loop yields something, and I don't explicitly specify what the left-hand loop is, and so that's why I'm a bit confused here. So let's just sort some stuff out. So I believe the loop that I'm referring to, if I had to venture a guess, would be starting from here, going down here and coming to ground. So starting at this ground and going around that loop. So I have VBE2 is equal to I1 times R pi 3. So that bit makes sense to me. And then I'm taking the voltage drop across R01. And this is the part where I'm having difficulty following my notes. Okay, no, I don't have any problem now. Okay, so in the previous step, we said that this current GM1 times VBE1 is approximately equal to I2. So let me just put this in right here. So if this current is approximately I2, then the current that's flowing through that resistor R01 should be I1 minus I2, doing KECL. There we go. Okay, sorry for the brain fart there. We can substitute in the relationship that VBE2 is equal to I2 over GM2. So that gives us I2 over GM2 is equal to I1 times R pi 3 plus I1 times R01 minus I2 times R01. And then moving stuff around, we wind up getting that I2 times R01 plus 1 over GM2 is equal to I1 times R01 plus R pi 3. And from this, the ratio of I1 to I2 comes out to be R01 plus 1 over GM2 divided by R01 plus R pi 3. which will be approximately equal to 1. Well, we're effectively assuming here that R naught 1 is much greater than 1 over GM2, and that R naught 1 is much greater than R pi 3, both of which should be the case. And also, intuitively, I1 and I2 should be very close to each other because this is a parent mirror, and that's the state. All right, so if I1 and I2 are equal to each other, or approximately equal to each other, then that means that I1 is equal to I2 is just half of our test current, IX. So IX splits evenly between both paths. And so now we can find our output resistance by applying Kirchhoff's voltage law around this loop. So going from here to here, right? And so that's going to look like our voltage Vx is equal to the voltage drop across resistor R03. So let's look at what that's going to be. That's going to be our current IX minus GM3 VBE3. Plus voltage VBE2. What's VBE3? Negative I1 times R pi 3, right? Using this good old Ohm's law. Minus GM3 negative I1 R pi 3, close parentheses here. I2 over GM2 goes here. And now everywhere we see I1 or I2, we can just replace that with IX over 2. So that'll be R naught 3 times IX plus GM3 R pi 3 IX over 2 plus IX over 2 GM2. And lastly, we see that R out is VX over IX, comes out looking like R naught 3 times 1 plus, do it like this, 1/2 GM3 R pi 3 plus 1 over 2 GM2, which will be approximately 1/2 GM3 R pi 3 R naught 3. Where we're just making an assumption here that this term is going to be larger than R naught 3 by itself, and it's going to be significantly larger than 1 over GM2. We're effectively throwing that guy away and throwing that guy away. And that should make sense, because what's GM 3 times R5? What's GM times R5 always? Beta. So we have a factor of half of beta multiplied by R0 3, so that will be definitely larger than R0 by itself, and probably way larger than 1 over twice G. So this guy has a significantly larger output resistance, and it introduces significantly less error. So it's a pretty darn good current measure. All right, we're 2 minutes over, so I'm gonna shut up for today. And we'll finish up current mirrors and start Cascode on Wednesday. I'm about to go to my office and work that homework 1 solution out again, and so I will update that stuff here before my next class at 2 for sure.